So today we'll start lecture 60 on the binary genetic algorithm, and essentially in this chapter we are going to build on the infrastructure we defined in the previous few slides or previous few lectures about the different aspects of GA, such as creation of the mating pool, performing the different crossings and mutations and so on, and then finally lay out the process by which you can write a computer program for the binary GA. And again, this is lecture 60 of my optimization series. I am Dr. Ranjan Ganguly, and the material follows some of the aspects in chapter 7 of my book. Now we have seen that once the reproduction process has been performed, the population has changed, and a new population is essentially created. The parents have led to the children. So in GA, actually the children supersede the parents. Now what you need to do is you need to check the fitness function value for each member of this new population, and then you find out what is the highest fitness value at a given k and the corresponding design variable which yields the highest fitness value. Now you do this at each generation, and here we are using k to track the different generations which are going on. And once this has been done, a generation of the GA is now complete. So the process of creating the mating pool, doing the crossing of the genetic material, and applying mutation leads to the new population, and then essentially a generation of GA is now completed. Now at this point you check if the number of generations has exceeded the maximum number of generations which you have specified. That may be something like 30 to 50, and in that case you stop the GA. And now what you do is you take the best function value and the corresponding design point across all these generations, that is the k values, and select that as the optimal point. So this is interesting in that in genetic algorithm, your optimum point may have taken place many generations before. For example, it could have taken place at generation number 10, and you may have been going on beyond that, and finally you may have reached the maximum number of generations and stopped. So this is not like gradient based method where typically you are decreasing the function value at each k because you are actually satisfying a descent condition, so you keep going downward. Now beside the maximum number of generation, you could use some different convergence criteria also. For example, people use the fact that if your function value is stuck, there is no change taking place in your function value f max k for several generations, then you could terminate the GA. Now this situation, if it happens, typically means that two things are possible. One is that GA has found a solution, and second is that GA is stuck in a local minimum. So both these things are likely to happen. Now if you have encountered any of these situations, then what can happen is that you could escape from this situation by a random mutation or crossing that may result in a solution suddenly becoming better. So this is of course a possibility. So you can never say anything about a GA because mutation keeps going on. Now if the best point does not improve in about 10 generations, then it is better to terminate the GA and run it once again with a new starting population. So this is something to keep in mind, is that you don't want to waste your time across the generations, because do remember that every generation is carrying along a lot of function calculations with it. So one of the things you find if you practice a lot with GA is that GA is very sensitive to the appropriate selection of different parameters, specifically the population size and also the cross over and mutation probabilities. So these are certain things to keep in mind. Now if you go through the papers, there are a plethora of papers which use genetic algorithms on different types of test problems as well as on different engineering and business problems. And this has resulted in a large amount of literature, and people have figured out the optimal parameters for each of the problems they were doing. And one thing you will see is that the optimal parameters of GA are typically problem dependent. And what I find is that typical recommended values include, for example, population size of 20 to 30, the crossing probability something like 0.75 to 0.95, the mutation probability ranging from 0.005 to 0.01. Now, these are some numbers which I have encountered quite frequently, and what you could do is you could experiment somewhere around these values. So this could be a baseline value with which you start, and then you could experiment typically around these values. So one of the main things here is there is always a trade-off between population size and the number of generations which is there in the given problem. Now, if you are increasing the population size very dramatically, you may get a good solution, but then partly you are moving to more of a complete search of the design space rather than using a particular stochastic optimization method to move in the design space. So that is something to keep in mind. Now, the strength of genetic algorithm typically comes from two factors. One is that we are throughout using probability in the form of random numbers at every stage of the process. So this is something which is very important to keep in mind. This probabilistic nature of the process is one of its powers and one of the sources of its power. Second fact is that we are working on a population rather than one point. And keep in mind that we are carrying this population throughout the process. So as reproduction happens, the parent strings are replaced by the child strings. The child strings then become the new parent string, and this process continues. So it is just like human societies. Essentially, the population keeps going on from generation to generation to generation, and therefore a plethora of fitness values need to be calculated. Now, this is very different from a traditional gradient based method where you are dealing with one point, and so you started with a starting point and you continue like that. So from its basic structure, you can see that a genetic algorithm is likely to zoom into a global minimum with much greater probability than a traditional gradient based method which starts from only one point. Now let us look at some of the philosophical aspects of GA which make it successful and quite powerful, and which also then led to the formulation of so many other stochastic optimization methods we will discuss later. And all of these share a certain philosophy which is coming out of GA. Now, first we see that the initial population is typically created using random strings, and you may mix some deterministically obtained strings also here. This of course gives a head start to the GA because it can look at different parts of the design space. Now you typically take a subset of this initial population by taking some of the best strings here. So this is somewhat of a culling which you do at this point, where you actually start out with the decent set of strings and then you work with these strings. So essentially the process such as reproduction favors the good string. So for example, whenever we are doing the mating pool creation, whether by tournament selection or by roulette wheel selection, we are favoring candidates with better fitness function values. And again, in this mating pool process, we are also using random numbers everywhere. If you recall the different methods for tournament selection and roulette wheel selection. So the randomness is present in this particular selection also, in contrast to actual situations in some cases. So now as far as the crossing of genetic material or bits between two good strings is concerned, the hope here is to get better strings, and this is typically the hope in a reproduction process also, where in any species the good candidates in terms of the males and females get together and produce an offspring. The same thing is being duplicated here, and it is generally hoped if the parents are in good condition, in good health condition, then the children will also be in a better health condition. So here we are measuring that health or that possibility of survival by using the fitness function. Now Mutation will change strings randomly here and there, and this is going to lead to local changes in the population. So in general, mutation may not result in a better string, but there are situations where it could allow you to escape from a bad situation. So in both of these cases, I have mentioned that neither crossing nor mutation is guaranteed to give only good strings. In fact, there is only the hope that they will give good strings. However, bad strings will be removed in the next generation of the population. Now that is something which GA ensures, because this new population is again going to be subject to that same roulette wheel selection or tournament selection and the selection of the mating process. So again, if the fitness value of the string is very low, in the next generation it is going to get wiped out. So this is very similar to what we see in society and in different situations, is that just because the parents have a lot of clout or have a lot of fitness doesn't mean that the children or the grandchildren will be at the same level. So this is a reality of life, and it's also a reality of GA. Now, one thing which you see by reading the different papers is that people typically run the genetic algorithm several times and then they take the best solution from the runs taken. So I have seen people sometime running it 10 times, sometime 20 times, some people even run it as much as 50 times. So one of the advantages of this approach is that each run starts from a different random population, and therefore the probability of locating the global minimum becomes more if several runs are done. So this process is probably better than using a very large starting population. So it is better to use a smaller starting population of something like 30 to 40 and perform several runs of the GA in most practical situations. Now we see that in contrast to the gradient based methods we discussed before, one of the aspects about GA was the use of random numbers at every stage of this algorithm. So right from the generation of the population where we use random numbers, to the creation of the mating pool where we use random numbers, to crossing point locations and so on, we use random numbers, and then mutation also, we were using randomness everywhere. And that is why GA is known as a probabilistic or stochastic optimization method. And this philosophy carries on to more modern methods such as particle swarm and so on, where you always use random numbers in different parts of the process. Now, the use of probability is both a source of strength and weakness as far as GA is concerned relative to gradient based method, because it does not give you the deterministic certainty which is present in gradient based method, in that these methods are going to follow exactly the same path if you run them twice, or they are going to move from one point to the next point to the next point and so on. Now, real life of course doesn't work like a gradient based method. That is a very tunnel based or tunnel vision approach of looking at the world, and so I would say gradient based methods are tunnel vision based, and in some cases that may be better, because if you are knowing your problem very well, or if you are in a field where you exactly know the path to take, for example you are a university professor, then the gradient based method may work out very well for you. But in the real world and Darwinian society outside the realms of universities or research centers, the world is generally functioning at a level where genetic algorithm type approaches are going on, and so any kind of probabilistic or random approaches are likely to be better. So now we are in a position to write out the binary GA as a set of steps which you can use to write a code for this problem. So the step one of the process would be choosing a coding to represent the problem parameters. So remember, coding, we mean that 4-bit, 8-bit, and so on. So each design variable has to be coded. Then you pick a way to select the mating pool. So here we studied tournament selection and roulette wheel selection. You choose one of these methods. You choose a way to cross the genetic information, and you choose the way to develop a mutant in the particular population. Now, next step is to choose the problem size n, crossover probability Pc, and mutation probability Pn. Now create a random or semi-random population of strings based on the move limits of the design variable. So this initial population can be of size 1.2n to 2n, and you take the best n values of the population to create the actual starting population here. And also you choose the maximum generation number k max, something like 50 could be chosen, and set the current generation k equals 0. Now in binary GA, step 2, if k is greater than k max, select fx star equals max of all these values. So these are all the maximum function values across the first, the second, the kth generation to the k maxth generation. So among all these, you find out which is the best fitness value you have obtained till now, and then you take this value. So this step is performed at if k is greater than k max, and this step is put here so that you can exit the algorithm in case you have exceeded k max. Now once you have found the best fitness value across all these possibilities, you find the corresponding x star as the optimal point and then stop. You also calculate the fitness function f corresponding to each string x in the population. So this is if you have not got out of the situation, you have not stopped. If k is less than k max, then you continue with these steps here. So you calculate the fitness function of each string and you are at generation k, save and store the fitness value, the best fitness function value, that is f max k, and the corresponding design variable x max of k. So remember that this x is a vector typically, so you may have to move from the string space in binary numbers to the real number space here. Now step 3 is you look at what is the possibility of creating the mating pool. So again you use any of the methods we have reviewed before, like tournament selection or roulette wheel selection. So you do this mating pool creation. You may keep the best value of the string shielded from the mating pool, so you may just let it survive for the next generation. And again, like I mentioned, you can use modified roulette wheel or tournament selection. Now once you have developed the mating pool, you subject this mating pool to crossing of the bits involved, and again you can use 2-point crossing on the selected strings in the mating pool, perform random mutation on very few members of the population based on the mutation probability. So this random mutation ensures that you are capable of getting out of a rut if you have got into in terms of the strings becoming very similar. And then after this step 4 and 5 are performed, you change k to k plus 1, that is you have moved to the next generation. You go back to step 2 and you then continue doing this repeatedly. So each time you do this, you check whether k is greater than k max or not. If not, you continue doing this till k max, and at the end of k max you get out of the GA formulation, and at that step you will have a hopefully a good population size. So today what I discussed will help you to develop a code to write a program for genetic algorithm, and this is a very good exercise you can do in any of the computer languages you may be knowing, whether it is C, Python, Fortran, Pascal, and so on, Julia maybe. And I would suggest you try to do this in an actual programming language so that you get a good feel about that programming language also. So I think if you have come this far in the course, you hopefully know a programming language and you can do some of these problems in the programming language itself. So if you go to my book, you will find that some examples are there which I have done using GA. So I have actually done a complete example by hand, and I have laid it out in terms of finding the optimal value of a function, so you can check out that example. So this culminates binary GA lecture 60 of this series, and I will meet you in my next video where I'm going to discuss real coded genetic algorithm. So that is going to be a very interesting topic. See you then.